Yes, I am.
My whole family's rich, it's not just me.
That's like the boundary. Maybe you have to probably define it.
That didn't sound bad at all. Such a sound.
That's your one some cereal you need
Tyler.
You really want some cereal?
How old is it?
I just had some this morning for
What's your
breakfast.
Oh, if you're gonna eat it, I won't take it.
There's not much left. If you want it, take it.
No, you can have it for breakfast tomorrow.
No, I have McDonald's tomorrow because it's Friday.
McDonald's?
Bro, that's a great tradition.
You're gonna get
Oh, every Friday morning. Sausage McMuffin, Dr. Pepper, one breakfast burrito with mild sauce.
That sounds, I mean, I probably double it, but like, yeah, because.
Oh no, my Apple Pencil Pro is dead.
He has issues.
I don't understand.
Just ignore it.
Why wouldn't you?
I really
You have rubber and aluminum foil, it can replace it.
Okay.
What?
Here's what we've got. So, one of the things that, if you look at the history of science, one of the things we struggled with, and we'll spend a lot more time talking about this, is that, like, what is the nature of light? Is light waves? Is it particles? Is it wave-particle duality, meaning it has properties of both? And then, how do we handle parts of the spectrum that we can't see? So, this is just kind of a broad overlay of the entire electromagnetic spectrum. So, you have very extremes of this. So, you have radio waves, and these are the values of the wavelengths, okay? So, on the very, 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 very end of this spectrum, you have radio waves that have a wavelength of like 300 meters. 300 meters is like the length of 3 football fields, okay?
Anything
Now,
but metric.
the cool thing about radio waves is that because they have such a long wavelength, they travel through space and through atmospheres relatively unimpeded. So what that means is that if you look at the Earth, and we've had radio transmissions for about 100 years, more than probably like 120 years. So because radio waves travel so unimpeded, the Earth basically has been this beacon of signals for about 120 years that we've been transmitting out into space. So the thought being is that if there's any kind of intelligent life out there that has developed the capacity to pick up radio signals, they will realize, oh, okay, hey, this is the signal that's going to travel easiest through space because it has such a long wavelength. And basically we're this huge antenna in our solar system transmitting all these radio waves. And the idea being that somebody out there would hear that, recognize it, and send a signal back. Now, the other side of it is they might look at those signals and translate them and go, you people are idiots, we don't want to talk to you. Okay, that's the other side of it. That's one thought process about why we haven't heard from anybody else. It was like they listen and go, you people are dumb. You're on your own. Now, microwaves, okay? Microwaves have about 0.03 in terms of a wavelength, which would be about like this. So, microwaves have a much shorter wavelength than like radio waves do. But compared to the visible light spectrum, they're exponentially longer. So here's the bigger picture. If you look at the speed of light, and this is what we talked about yesterday, equaling wavelength times nu, or wavelength times frequency, the wavelength and the frequency multiplied together always equal the same speed of light. So what happens is that if you compare radio waves to, say, microwaves, those wavelengths are getting shorter. So as the wavelengths are getting shorter, what's going to happen to the frequency? Yeah. So as you go across on the spectrum, the wavelengths are getting shorter, so we're shortening the wavelengths. But in contrast to that, you're increasing the
Frequency.
But as you increase the frequency, what happens to the energy? It also increases. So we're also increasing the energy of the individual photons. So if you look at microwaves, okay, microwaves compared to visible light has a much, much, much lower energy than visible light does. But if you want to make a bag of popcorn, you know, hey, let's make popcorn, let's watch a movie. And you take a bag of popcorn and you shine a flashlight on it, what's going to happen?
Nothing.
It's going to look bright, but that's about it. But you throw it in a microwave, and that microwave has a lot longer wavelength and a lot lower energy, what's going to happen? It's going to pop. So here's what they figured out about microwaves. They actually found microwaves accidentally. The legend has it, a guy had a, we'll talk more about this later, a guy had a candy bar in his pocket, and he was standing by. No. And he was standing beside a radioactive source. He didn't know what it was, and then all of a sudden, the candy bar started to melt, but with no visible reason for it to melt. And so they figured out what these they didn't know they existed at the time. But what they figured out that microwaves do is that they match what's called the resonant frequency of water molecules. So all molecules have a frequency at which they vibrate, kind of like that wine glass. So that wine glass vibrates at a certain frequency. Water molecules vibrate with a certain frequency. And microwaves match that frequency and that energy. So the reason microwaves work is because they take those water molecules, and the water molecules go, ooh, this is the song of my people. And they basically begin to do this weird Scottish dance, you know, the river dance of water molecules. Don't. And so they begin to vibrate. And as they vibrate, that's what heats things up. So the reason that visible light, you shine the light on it and nothing happens, is because it doesn't match, the visible light doesn't interact with water molecules, which is why you can hold up a glass of water and light goes right through it, because the visible light doesn't interact with those water molecules, and they go, hi, how you doing? Cool. And they just go right through. The water molecule runs into that water molecule, and the water molecule goes, this is the song of my people. Let's do the river dance, okay? And that's the short version of why that works. So, then on the other extreme, you have like x-rays. So if you've ever broken a bone or had your teeth x-rayed, these are extremely short, high energy photons. That's what allows you to x-ray your hand. Again, it's the other end of the spectrum. Oh, I think I broke my hand. Hey, somebody go get a flashlight. Let's shine it on your hand. Okay, cool. Probably not going to happen because of the fact that that light lacks the ability to have enough energy to go through your hand, but that x-rays don't.
You can see through skin now. They've developed a thing.
Okay,
Using the pigment from Doritos.
shush!
Yeah, he's right.
You're using what?
Yeah, basically it's
use
Dorito
the
dust.
pigment from Doritos to make like the oils and like the proteins and lipids in your skin like homologize, like how like water and oil mix, and then it becomes transparent.
That's
It
disturbing.
is. It's terrifying. Just wait.
You
until,
want to
like,
see something gross, light a Dorito chip on fire. and watch that puppy burn. It's disgusting. Like, it's black, nasty char oil that comes out of that.
Just wait until 10 years when we figure out how to make that like a hip like beauty standard. Like you get tattoos that turn your skin clear.
Okay,
I've
there's a
had one
reason
tattoo
that
in my
skin is
life,
okay.
never doing another one. Okay. Now, what you feel as heat
Start dying.
is just beyond what we can see. That's infrared. That's why it's like, oh, is the stove hot? Don't put your hand directly on the stove. Put your hand a little bit above it. You can't see it, but you can feel that as heat. So what you feel as heat is infrared. Now, if you go out in the sun during the summer or even when this time of year with the snow, what causes sunburns is the other end of that spectrum, which is ultraviolet. Okay, so your ultraviolet light has more energy than your visible light. There you go. Now, what we can see out of this entire spectrum is actually a very, very, very narrow band of it. It's called Roy G. Biv. Hopefully, you've been taught this at some point. I'm not going to expect you to know it. Here's the two extremes. You have red light, which is about 700 nanometers, and you have violet light, which is about 400. So this is why fires glow red before they go out, and not purple, which would be cool, don't get me wrong. They glow violet, excuse me, they glow red, because that's the low end of the spectrum. That's the lowest energy. This is also why sunrises and sunsets are red, because red light, kind of like radio waves, can penetrate through the dust in our atmosphere easier than the other colors can. So this is why at dawn and dusk, the sky tends to be redder, because it's that red light that passes through and all the other ones get scattered. So here's the whole point of the story, is that all of them have this relationship. No matter what, radio waves, they all travel at the speed of light. So here's a common misconception. People go, oh, I hear the radio. That means that's sound, and it travels at the speed of sound, 343 meters per second. No, stop, okay? You hear the sound coming from your radio, which is traveling at the speed of sound. But to get that signal to you is a radio wave, which travels at the speed of light, okay? You remember that when you have a problem on your test, because I'm going to give you problems that involves radio waves. Do not use 343 meters per second as the speed of a radio wave. I failed to point that out the very first time I taught this class. And I had kids that were using 343 meters per second. And they were getting answers to a calculation that put them beyond the other side of the moon, which is, if you look at one of those shirts up there, there's like kind of a picture of a moon, and that's because they had to figure out how far like a boat traveled in between, how far it was offshore, and the kids were literally getting an answer bigger than the distance to the moon.
But
And it was
bird
like,
camp, we won't.
did that not cause you pause that you were getting an answer of 10 to the 9th meters for how far the boat is from the shore? We thought it seemed a little big.
We're American. We don't know what 10 to 9 meters feels like. They need to give it to us like distances to the nearest McDonald's.
But bird camp, we won't do that.
Anyway, so that's one of the reasons I point that out. Now, one of the things we figured out is that we can use solar panels, oddly enough, and hook that up to a speaker.
Stop, I just made that straight.
The son of the
Okay.
sun.
Now, here's just your basic remote control. So it sends out a signal that conveniently you all can't see. It isn't like I'm turning on a flashlight and you all see, oh, I see it, okay? But if I direct it towards the solar panel, when I push the button, it's emitting a form of electromagnetic radiation that the solar panel recognizes. And it excites those photons within the solar panel, and that changes it into sound. So you can't hear the difference, but every time I hit a different button, there's a very, very slight change in the frequency of the radiation that's being emitted. And your TV picks up that signal and goes, oh, you want to turn to ESPN, or you want to watch Netflix, or whatever that is. So your remote is sending out a signal. You can't see it, but there's a receiver somewhere that picks up that signal and changes it into an electrical signal that then does something. So when I pull this away, what happens to the intensity of the radiation that's impacting the solar panel?
It decreases.
So there's an inverse relationship,
Yeah, cool, sure.
right?
Yeah, that sounds right.
So when I'm close,
Yes.
it's very intense. When I move further away, it feels weaker. Right? Okay? So clearly there's an inverse relationship. So we kind of got to go old school on this concept and work in some old school units. Okay? So when you look at intensity, so intensity, shown by the letter I, is power per unit of area. So, Will Stanley, do you remember the units of power?
That was
Can you be hand starts with a W?
Joule. Oh. Watts.
Watts. No, watts. That's just it.
Watts.
Watts.
Watt.
Okay.
Watt.
Now, watts are joules per second. Okay. But power itself is just watts. So the area, oddly enough, is going to be measured in meters squared. Okay? Now, to get the area, there's two ways that you can view this. To calculate that area, if it's a point source, like this, a light bulb, the sun, whatever that is, that area calculation is 4 pi r squared. Okay? So basically what you're doing you're treating it as a point source, and that wave is getting further and further spread out. So if you double your radius, what's going to happen to that area? It's going to quadruple. So now, if you're talking about the other side of that, like if you're talking about like your eardrum, okay, and you're talking about how much sound strikes your eardrum, then that's a circle, and that's just pi r squared. So and this makes sense because you're going to have problems like this on both sides on problems. So it'll say, hey, you know, what's the intensity of sound if your eardrum has a certain diameter and the wattage that's being produced is like 5,000 watts or whatever that is. What's the intensity hitting your eardrum? So if it's a point source like the sun emitting light, you use 4 pi r squared. If it's an area hitting like your eardrum, your eyeball, something like that, then it's pi r squared. Now, typically what you want to do is compare different intensities. So we're going to do a little bit of voodoo. So to compare two different intensities, and don't worry about writing all of this down. I'm going to show you the nuts and bolts version of where this ends up. So that's going to be the power of the source divided by 4 pi squared. Hold on. Okay, so this would be a situation like this where I say, all right, then I've got this solar cell, and I know at a particular distance, there's a certain intensity. So then if I move it back to a different distance, I want to figure out what that new intensity is going to be. Now clearly, the new intensity as that distance gets bigger has to be smaller, okay? So, if you compare these, if you look at this in terms of the power from the source, this, as long as it's the same, like the same remote control, the sun, the light bulb, something like that, these are going to be the same, and those are going to drop out. So if you have the same source, which almost all the time you are, that just drops out of the equation. So then you've got the same 4 pi, that's going to drop out of the equation because it's just a ratio. So if you do some voodoo, and that R2 is going to flip up and that R1 is going to come down, then you get R2 squared over R1 squared. And if you go through and solve this for I2, you get I1 times R1 squared over R2 squared. Okay? So this is kind of your functional version of this. Now, if you have a remote control for your car, you deal with this equation, okay? It's like, Burkamp, we've never seen that equation before in our lives. But look at this, right? So, as R2 gets bigger, okay, so intensity 1, you would be saying, hey, you know at a certain distance, this is the intensity. And you're going to know R1. So your variable typically plays out to be R2. I1 is a given value, R1 is a given value. R2 is going to be your variable. So you all know that you have to be a certain closeness, there has to be a certain proximity to your house for the garage door to open, right? You can't be here in the parking lot of the school, be 3 miles away from your garage and hit the garage door button and it's going to open, okay? It's not.
I was trying to explain Doppler effect to Thatcher real quick.
It's
We'll
in the
get to
book.
that today.
Okay.
So, if you have a proximity, if your car operates off of a proximity key, it goes off of this equation. So basically, if you let R2 get too big, you're too far away from your car, it won't recognize the key. It won't open the door. The car won't start. Your garage door won't open, okay? It's the same thing of your cell phone. If you go out in the middle of nowhere, what happens to your cell phone coverage?
It drops.
It drops because of the fact that you're too far away from the...
Look, a cell tower.
Now, the same thing plays out, oddly enough, with solar panels. So if you look at the sun, okay, well, here we are on Earth. We're kind of at a sweet spot in terms of intensity of light from the Earth. Well, if you're out here on Mars, solar panels won't work as well. Why, Cohen?
You're too far away from the sun.
So what's going to happen to the intensity?
It goes down.
It goes down, okay? Now, things that orbit the Earth, like the International Space Station, that's cool. We can use solar panels to charge them. But if you're going to send probes like Saturn, Jupiter, planets that are further out, don't equip them with solar panels. because they're gonna be so, the light is gonna be so spread out that the solar panel won't do you any good. Okay. Now, let's talk sound intensity. Don't worry about this. If you need this equation, I will give this to you. I'm just explaining what it is. If you look on page okay, so on page 486, sound is measured off what's known as the decibel scale, and I'll go back and I'll show you what that sounds like, no pun intended, in just a second. But if you look on page 468, it gives you these different values. So I naught is like the baseline, okay? So that's like the absolute lowest threshold of sound energy that humans can detect, okay? Boom, that's your baseline. So if you look at person breathing at 3 meters, 10 decibels, residential street, normal conversation, threshold of pain, 130, okay? So, let's go to the back of the room, and I've got a decibel meter, and I'll show you what that looks like. So Andrew, stop that camera, bring that back.